So for today, the topic that we're going to be sharing on is Introduction to Deep Learning. But then there is a certain emphasis and certain slant towards that in the COVID-19 situation. But first, a little bit about myself. I graduated from NUS back in about 10 over years back. And then thereafter, I went to so-called master's in Singapore MIT Alliance and followed by PhD in Imperial College. After my PhD, I went straight into industry in A-Star. I've worked for about 15 over years deploying and so-called implementing IT solutions. The last 10 years were especially on AI-based solutions. So some of the companies I work with or rather have projects with, like ExxonMobil, Visa, MOF, JTC. I was a adjunct at SIT from 2017. About a year back, 2019, I joined as a full-time assistant prof. So here we are today. In place of a physical face-to-face seminar, we have instead a virtual seminar. And I'm sure in the workplaces, in place of face-to-face meetings, right now you also have virtual meetings. In place of physical documents, you now have virtual documents. What this means is the following. For your meetings, instead of just meeting minutes that are being captured, entire meeting conversations, including audio, text, and video are now being captured. In this virtual seminar, every single word that I'm saying, every single question that's being asked, every single question that's being answered, every single expression that I'm making, every single mistake that I'm making as well, is all being captured and digitized. Same goes for that in your digital documents. So what does this actually mean? This definitely means that there's going to be a huge increase in the digital data that's being generated. But digital data alone doesn't account for much. It must also be counterbalanced by a rise in technology in order to analyze this type of digital data. And here I quote Professor Andrew Ng, which is a professor at Stanford University. He came out with this graph a couple of years back, where he compared between classical machine learning versus that of deep learning. For classical machine learning techniques, what we have found is that the performance of them, it plateaus after a certain point of time. However, for deep learning techniques, we are still seeing the increase when more data comes in terms of the performance. Over the last 4 minutes, I've brought about 3 technical terms: artificial intelligence, machine learning, and deep learning. So over the course of this short sharing, I'll be going into detail about these 3 terms, and hopefully by the end of it, you'll get a clearer understanding of what do these terms actually mean. But first, we have artificial intelligence. What does AI mean? I'm sure we're all very familiar with Jarvis from Iron Man Avengers series, Terminator from the Terminator series, C-3PO from Star Wars. These are AI that seems to be able to do whatever a human being is able to do. And typically, we term this form of AI as general AI. The other class of AI is that of narrow AI. For example, we have AlphaGo, who defeated the world Go champion. We have spam filters that we use in our daily lives, which help to sieve out the spam for us in the emails. We also have digital assistants like Siri that helps to make certain parts of our life a little bit better. What narrow AI means is that for that particular domain where the machine model is being trained in, it is extremely good at it. But if you put it in another domain, then it will cease to function as well. What it means is that if I take the model trained in AlphaGo and put it into a spam filter, it will not be able to catch spam. It will probably not be able to catch spam at all. Likewise, if I use the model trained in spam filters, put it in the digital assistant, it will not be able to function as well. What we have today is we have a better performance, or rather, we have more advancement in terms of narrow AI rather than general AI. And that will be the form of AI that we'll be focusing on for the rest of this session. For narrow AI, we have 4 different categories as well. And in this, we point to one of the authoritative texts, which is AI, a Modern Approach, published in 1994. So in these 4 categories, the first category is that of thinking humanly. And this probably sparked one of the first so-called motivation behind that of neural networks into modeling how does a human brain actually works. Today, we have so-called technologies such as systems biology in this category of thinking humanly. The second category is that of thinking rationally. That is primarily mathematical formulas consisting of first order logic. The models created there are primarily, they call them deterministic, meaning that given a specific input, I can always expect the same outputs because these are all determined by mathematical formulas. Of course, the challenge here is the following. These formulas are very hard to be written in a fully closed system. It's really hard to take into account of all the conditions and then to convert them into mathematical formulas. The third form is acting humanly. We now have subjects A, B, and C. What we see in the image there is known as the Turing test. In the Turing test, A is a machine, B is a human, and C is a subject talking to both A and B. And in the Turing test, the objective of the Turing test is for the machine A to be able to fool subject C into thinking that machine A may be another human as well. Turing test, over the years, we have seen some limitations in that test. For example, all of us know that AlphaGo is in fact an artificial intelligence machine. But it does not dispute the fact that it is definitely a form of artificial intelligence. So we do see some limitations with this approach. The last one is that of acting rationally, whereby we have agents that maximize the certain expected value based on a certain measure. It may be historical data or other forms. And this is the category that we'll be focusing on because it entails two key categories that we always encountered with, which are expert systems and machine learning. These two forms are always confused with one another. And let's try to delve a little bit deeper into these two forms right now. First, we have expert systems. For expert systems, primarily, you have a domain expert that comes up with these rules. So firstly, you have a domain expert with the rules that's being generated. You have the data as well. These are fed into the machine and you generate a certain output. Let us give a simple example. Let's say if I want to detect the number 8. So how do I determine that this is showing the number 8? A very raw algorithm can be, I divide the image into the top and the bottom. If I see a circle at the top and I see a circle at the bottom, I will say that this is the number 8. Definitely this algorithm, however raw it may be, it may work in certain cases, but not all of them. So for example, this image here, it is, to a human being, it is clearly the number 8. However, the circles are not really seen to be very, very clear. And so this kind of a rule-based expert system approach will most likely fail. Similarly, if I have a mahjong tile with 2 circles, this is definitely not the number 8, but it may be misinterpreted by the machine to mean the number 8. On the converse, we have machine learning algorithms, and the point of view of them is very, very different. What it does is that it takes the data, it takes the output, and the machine generates out the rules or the models. What it means is that, let's look at the first piece of the data. This is a handwritten piece of numerical numbers. Every single column is a piece of data that's being fed in. So the first column is how a person will write the number 0. Second column is how a person will write the number 1, and so on. This is the data that's being fed into the machine. What then is the expected output? The box in blue is the expected output. So for the first column, if I were to feed into the machine this handwritten column, I'm going to expect the machine to give me this is the number 0. Likewise, for the second column, if I'm feeding in the number 1, I'm going to expect the machine to tell me this is the number 1. And the black boxes will be the data. The blue box is the output. And from this, we then generate out the rules. The rules for how to determine that from the data, I'm going to get the output. So notice that in this entire cycle, the human being is actually devoid of making any decisions onto what the rules may or may not be. They are responsible for making sure that the data is correct, for making sure that output is correct, but they are not so-called, they are not hands-on in crafting out the rules at all. So we have also, the example I showed earlier is that of supervised learning. We have two other types of machine learning: unsupervised learning, reinforcement learning. For today, we'll only primarily be focused a little bit more on supervised learning. And so with that as the backdrop, let's go a little bit deeper as well to see what deep learning is. So maybe as a very brief recap, we talked about AI in general and narrow. In narrow, we have four parts. We talked about only one part, and that portion is on primarily machine learning. And now we're looking into deep learning, which is a subset of machine learning. So we come back to this so-called graph again. And the first model in machine learning we're going to look a little bit deeper in is on linear regression. For linear regression, let's go back to when we were maybe in our secondary school. I hope some of you remember that we used to do this experiment often where we have a pendulum, we let it swing from the left to the right and then to the left again. And at the same time, we will adjust the length of the pendulum. And the objective of our experiment is the following. If I were to change the length of my pendulum, would the period of my pendulum be affected by it? Okay. So recall this was an experiment that we did in our secondary school. So what are we measuring? We are measuring the time it takes for the pendulum to swing from the left to the right and to the left again, and we are adjusting the length of the pendulum. This time for the pendulum to swing from the left to the right to the left again is known as the dependent variable. And it is very intuitive why it is called dependent variable. Because it is dependent on all the other variables that may affect it. For example, the length of the pendulum or the weight of the pendulum. Hence, it is the dependent variable. We are adjusting the length of the pendulum, and that is known as the independent variable. Why is it independent? Because it's not affected by all the other variables around it. So I'm using my length of the pendulum to see how it affects my dependent variable of my period of a pendulum swing. So if you were to recall, you will be adjusting different lengths of pendulum you see the table over there in the first row, we have X, which is my length of the pendulum. I'm adjusting 1 centimeters, 2 centimeters, 3. And when I adjust those lengths of pendulums, I will then measure what is the period of the pendulum. And that you see in the second row in the table over there. You will then plot a line graph and you will draw henceforth a line of best fit. So essentially what we were doing was linear regression. So we are actually trying to find out what is the best relationship that we can draw between my length of the pendulum versus the period of the pendulum. And you will recall that we will then derive this line, which is y equals to mx plus c. And what we are learning from here is the gradient of the line, which is m, and the y-intercept, which is the value of c. So this is the first base model of machine learning. And from there, we build on deep learning so-called techniques. So if we dovetail back to what we talked earlier about machine learning, the data is my first row, which is my varying length of my pendulum. And my output is the period of my pendulum. So the first is my independent variable, and the output is my dependent variable. And I use it to generate out the rules, which is y equals to mx plus c. And I reproduce it below in this representation where I have a box x, a box m, and this will mean x multiplied by m plus the value of c to form the output variable of y. And in the entire model, we are learning the variables m and c. Hence, we have the term machine learning because we are really learning some of these variables. Okay. So if we put it back here in this graph, this is the first model of linear regression. Okay, let's go a little bit deeper to find out what happens if there's more than one independent variable. If there's more, and we will have done it as well, let's say we want to measure the period of the pendulum swing. But this time, we adjust not only the length of the pendulum swing, we also adjust the weight of the pendulum. And so we not only have one independent variable, but we have two independent variables right now. And if we were to plot the graph here, you notice the gray table, we have the first row is the varying length of my pendulum. In the second row is the varying weight of my pendulum. The third row is the varying period of my pendulum. So as an example, in the first column, my length of the pendulum is of length 1 centimeters. My weight is of 10 grams. My period is of 2.6 seconds. Likewise, for the second, it is 1 centimeters of 20 grams and 2.4 seconds. And from then on, we also create a graph of y equals to m1x1 plus m2x2 plus c. Or we have the y equals to summation mx plus c. Okay. So this occurs if there are multiple independent variables that are in the equation. Likewise, the data that's being fed in is all my independent variables. The data that's fed as the output is my dependent variable. What is my expected data that I am supposed to see? And the rules that are being learned are the multiple gradients and the multiple y-intercepts that may be there. So if we put it back into our earlier representation, we have to learn the variables of m and that of c, and to convert it into this form whereby I have multiple values of my input independent variables of x together with my gradients. I add it with my y-intercept to form the formula in my red colored box to have my output variable of y. So this is the second model in multiple linear regression. The next step that we're going to cover will be one step on top of multiple linear regression, whereby in place of the red color box with my y, I have something in between. And right now we're going to show that as a neural network of a single layer perceptron, which is the base model of a deep learning model. So for that, let's go back to our multiple linear regression first. So we have seen this earlier. We have multiple values of independent variables of x, that of m. We also have the y-intercept of c. We have the output variable of y. So what this single layer perceptron does is, in the middle of this, we have they call it the non-linear activation function. I will speak a little bit more on what this non-linear activation function is very shortly. But what we have is that we have this as we also are learning the variables of m and the variables of c as well. So what does this non-linear activation function mean? Let's illustrate that with a simple example. Okay, let's supposingly we are ordering food from a so-called fast food restaurant. If I have $1 and I'm able to buy one burger. For $2, I'm able to buy two burgers and so on and so forth. So every time the amount of money I'm spending increases, the amount of burgers I'm getting is linearly dependent on the amount of money that I'm spending. So I have $5, I can buy 5 burgers. $3, I can buy 3 burgers. What does a non-linear function mean? A non-linear function will mean something like the following, where I'm buying a meal. Let's say I buy a meal of $5. This is a single meal, is $5. And let's say I'm buying a family, so-called a double meal. It may cost me $9. So notice that now I'm getting twice the amount, but I'm paying less than twice the amount. So hence there's this non-linearity that is occurring. And if I'm buying a family feast, I'm For example, I'm getting 4 times the amount, but I'm only paying 3 times of that of a single valued meal. And if I buy a party feast, for example, I'm going to get 6 times the amount, but I'm only paying 4 times that of a single value meal. So this is what they mean as a nonlinear function. So why is this nonlinear function so essential? It is important because in theory, we have seen that if you have a neural network, you're able to represent anything from the output based on the input using a non-linear function. So conversely, if you have multiple neural networks, stack one atop another, if they are linear functions, they can be decomposed into one single linear function. So some of these examples of nonlinear functions in neural networks are the following. We will not go into detail what these are specifically, but if you were to see them, the first one is the sigmoid, the 10H, the ReLU, the leaky ReLU. So these are some examples of nonlinear activation functions in neural networks. Okay, so these are the three so-called building blocks behind deep learning. So these are still considered as classical machine learning techniques. And now we have the right foundations to try to understand what exactly deep learning is. So this is an example of a single layer perceptron in the midst of an entire deep learning model. At the same way, the blue colored circles are my input independent variables, and the red colored is my dependent variable. So you can imagine that this is similar to that of my multiple linear regression model that we have introduced a little bit earlier. At every single node, my neural network will learn the variables. So both the gradients as well as the y-intercept. And hence there's a term deep learning. And why do they call it deep? Because it has multiple layers in my deep learning model. And hence they call it a deep learning model, hence the term. So this is what an example of a deep learning model looks like. So in this, there are two hidden layers. So the dark blue is my input independent variables. The green color is my output dependent variables. So I have also the red nodes and my light blue nodes. Every single line that you see there is a single layer perceptron. And so we are composing multiple layers of single layer perceptrons together. And hence, you can consider a deep learning model to be just a few layers of or single layer perceptrons that are stacked one on top of another. And one of the key thing is that there must be a non-linear activation function separating between such linear models, or rather separating between such single layer perceptrons. Hence, right now, when we go on to back to our graph that Andrew Ng brought up in the very beginning, we have now classical machine learning models. They plateau at a certain point, but it is exactly this form of deep learning that enables your variables to be learned in a very rich and diverse manner, such that the performance is able to improve when more data is being supplied to it. So I'm going to illustrate this with a few examples. But before that, let's do a short recap. We talked about AI at the very, very beginning, followed by narrow artificial intelligence, which is a subset of what AI is, where AI, we are concentrating on various tasks that we want to be able to do. Within narrow AI, we then have machine learning, which is really how we can take in the data, take in the expected output to generate the rules or the model. And from machine learning, we talked about single layer perceptrons, we talked about linear models, and we look at what deep learning is, which is a subset of machine learning, which is actually a stacking of various single layer perceptrons together. Let's try to illustrate what deep learning is in today's context with a sample application. Okay, so recall that we have this application at the very beginning where we have expert systems and machine learning, supervised learning technique. If we try to look into this in the deep learning context, this is an example of what we see. At the very top left corner, I have drawn a number 8 there. If you go a little bit down below, you can see the first guess and the second guess. What this means is that the first guess of my machine learning model is number 8, and the second guess is the number 0. If you look at the central figure, at the very bottom, you see the number 8 there. That is my input variable. Every single point, every single pixel that you see over there is one of the independent dependent variables. If you go all the way to the top, you have my output variable. The output variable is what the model is predicting the input to be. In this case, the first guess is the number 8. The second guess is the number 0. In the middle, you have multiple layers, and these are essentially your deep learning layers. If you look at my if you look at the first layer where I have lines coming in from my input to my second layer, you have blue lines that are emerging. Every single line there is supposed to be a single perceptron. So every single line is learning multiple values of my gradient, multiple values of my y-intercepts in order to, and each will have a nonlinear activation function. And using this technique of stacking per single layer perceptrons one on top of the other, we are able to generate a model that's able to very correctly identify, in this case, numerical digits. And they are done in a very accurate fashion. Let's use this with another example. Let's say that you have a book that you want to understand, but you really don't want to read the entire book. So how we use the analogy of deep learning is this: you pass it first to 10 people, and you ask these 10 people to give you a summary of the book. The condition is that the summary of the book must be shorter than that of the original book. And from then on, you pass it again to 10 people as well. And from then 10 people again to 10 people. So notice that every single layer that you're going, every single reviewer layer that you're going, you're actually going deeper and deeper and deeper. And every single reviewer is going to give you a slightly more condensed version of the original book. But the condensed version of the original book is done in such a way whereby it is to the reviewer's background and to the reviewer's understanding and interpretation. So you will then have multiple interpretations of the exact same book. And then you start to recompile all these interpretations together. You take out the ones that you think are more general or more pertinent. And at the end, you get a very good summary of all the so-called features of what the book is trying to tell you in this multi-layered review approach. That is very similar to what deep learning is. And, uh, and right now, I'm going to show you this example of how we can train deep learning models in a very easy manner. So in this example I'm showing you, this will be, I'm going to train a model that is able to differentiate between a ball and a black wallet. So I will show you the video, and as I'm playing the video, I'll also be speaking over it. The first thing I'm doing is that I'm going to on the webcam, and I'm going to hold up a black wallet. Excuse me. And now I'm going to collect multiple images of me moving the black wallet around. The second thing I'm doing is that I'm going to hold up a soccer ball. At the same time, I'm going to move the soccer ball around as well. And you may be asking, why am I moving the soccer ball around? It is because I'm trying to add variability to the training data. So as much as possible, I want the model to be able to see different variations of the ball at different locations. So I'm now training the model. Part of this video is actually sped up by quite a bit. So now the model is completed training. If I show up the black wallet right now, it shows that it's a black wallet. If I show up the soccer ball, it shows that it's a soccer ball. Okay. But do you notice something wrong with this? There's a certain bias to this model. Right now, I'm not holding up anything, but still the model is telling me that I'm holding up the black wallet. So this is where accidental biases may be introduced into the model that we might not have seen or realized before. So in this case, it is very so-called somewhat easy to see that immediately there is this error that's being generated. What we can do to resolve this error is that we can then add in one new class called the background model, which is what I'm going to do now. So this particular form of training, or rather this particular form of machine learning is called classification, where I'm classifying objects based on what they are seeing on the screen. So in this case, I'm classifying a black wallet, I'm classifying a ball, and right now I want to classify myself as the background. So I'm now collecting various images of me in the background. I train the model once again. And after the model is being trained, you will then see that when when we when I'm not holding up anything, it's showing up as the background. When I'm holding up the black wallet, it's now showing the black wallet. When I'm holding up the ball, it's now showing the ball. So right now, the machine model seems to be a little bit more complete, but still there are some issues with it. Why? Because I've only trained it with one certain type of a soccer ball. So there are various types of balls that are there. So for example, there are tennis balls, basketballs, there are smaller so-called ping pong balls as well. And in the next video, what you will see is that I'm going to show up a very small blue colored ball. And instead of the model saying that it is a ball, it's going to say that it is a black wallet. So I want you to focus on the window on the right side of the screen right now. So notice right now, I'm going to be holding a blue colored ball, and it's saying that it is a black wallet instead of a ball. At the same time, I'm now collecting data that this is a ball. So I'm right now telling the machine learning model that, no, you got it wrong. This should be a ball instead of a wallet. I'm putting it in my training data, which is my the data set. I'm retraining the model once again. And right now, if you see, if I hold up the soccer ball, it's a ball. If I hold up the orange ball, it's now a ball. And when I hold up the tennis ball, it's now a ball as well. So this is where the magic comes in. Notice that in my training, I only use the soccer ball as well as the small blue ball. But what has happened now is that the model is able to achieve a certain form of generability, meaning that it's able to generalize. It's no longer constrained to the data that I have fed it with. And that should be the aim of every machine learning model, whereby it is able to go beyond that which I have trained it with. So today, or rather in this model in particular, we are seeing it being able to identify, using just the soccer ball and the small little blue ball, is able to identify the orange colored ball, which is a little bit smaller, and also the large yellow colored tennis ball. And in the way we train machine learning models, we ought to try to achieve that when we are collecting the data, it should be as complete as possible, but yet we do not try to, in a way, overtrain it with too much, such that when new forms of data that we are expecting it to be able to capture comes in, we aren't able to capture them properly. And there's still one major bias that we see in this photo, or rather in this model. And that major bias is actually myself. So as I said earlier, I'm training the model to differentiate between a ball and a black wallet. But unfortunately, I'm in the picture. So I'm one of the biases in the picture itself, or rather in the training data itself. So fortunately, in this case, me as a bias, it didn't matter very much. If I were to show up, if I were to display the wallet or the ball without myself, the model is still able to function relatively well. So that is the fortunate case. But it may not be the case in our daily situation, whereby if let's say we are training model and there are certain biases that may be there that we are unaware of, the model may not be as forgiving as this one that we have seen over here. how is this being applied in our real life? In the States, this is one of the large chain mega marts in the States. And how they've done it is that they have used satellite imagery to find out how occupied your parking lots are, and to use the occupation of these parking lots in various timestamps of the day to determine to determine how much your revenue will be for that quarter. So this was done in a pre-pandemic era, whereby they managed to do this to pretty much accurately determine what is the revenue of a certain mega superstore for that quarter. And of course, there are also various different verticals that this can be applied to. I just shown you one very small segment. Of course, there's life science, insurance, hospitality. There are actually many parts of this whereby this concept of deep learning can be easily applied to. But what is really important is the following. Whenever we are trying to enact any type of change or any type of difference that we are doing, it's always very sensitive. So I remember one of the first projects I did when I was actually at about 20 plus years old. In the first meeting that I talked to the execs and actually they were very worried and they were very concerned. They asked me the question is, if you were to automate everything, what are we going to do? Yeah, or what they meant was that what will their job roles be if we were to automate everything? So that was a very early lesson in understanding about the how important uh, human nature is, or rather human change is to organizations, whereby we also really recognize that all organizational change is actually human change. And really, it's very important to get this human aspect correct, regardless of whatever digitization or optimization processes that we are set out to do. So one of the things that we have done over my years is that one thing is that we try to do very simple pilot projects first, and that is with the prime reason that we want to build trust with people. And building trust with people is actually very important, because then we're then able to secure very early wins and to let them understand that we are really there to help make their lives better. And I would reinforce this with another example whereby we want to solve problems in depth rather than in width. And why do I say that? Sometimes or rather usually the executives that are working with, they're going to be extremely busy with their work already. And if your life is to make them better, you want to be able to solve their problems that they're facing in as complete a form as possible. So you want to just focus on one or two of the most pressing issues to solve it as much as possible, and so as to help to reduce the time or the wastage of time that they're currently experiencing in their work. One of the experiences that we have is that if you try to solve multiple issues at the same time, all of the issues are going to solve in a so-called not in the most complete form. And what's going to happen is that the executives were going to be facing a technical issue. They'll come back to us, and this back and forth will occur a few times. And essentially, they will start to lose confidence in the entire project, and they will think that doing this project is actually wasting more time than saving their time. And that is the danger, and that's where a lot of such projects don't go as well. And finally, we always want to ensure that we communicate early, we communicate very often. We want to demonstrate our lives is really to make their lives a lot better. Yeah, and with that, I go on to the Q&A. Okay, so Mr. Kaysen asked the question of deep learning sounds like a very computational heavy task. Can off-the-shelf be used to do deep learning training and inferencing? Thank you for your question. So what happens is that definitely is very computational heavy stuff. What is done is that there are so-called free GPU resources that you can use for training. So for example, Google Colab has a free GPU resources that can use for about 6 hours at a go. So that can be used to kind of train quite a complete model already. For inferencing, your base laptops or whatever will be able to carry that out pretty well. So those are for so-called simple models. Definitely, if you want to build very complicated models, let's say if you want to build like 3 or 5 different deep learning models to be run concurrently, you may require the use of dedicated GPUs, which can be done through the cloud, which may be slightly better for that. Similar to your question, if you are talking about can it be able to accommodate inferencing? So once again, there are many facets to that. It just typical inferencing, you're able to do it. But yeah, if you're looking at what is the expected volume of requests that you are going to that you're expecting to see. So that is another big question. So yeah, if you're expecting to see a huge volume of requests, then definitely your own laptop won't be able to support that, and you will need a proper so-called a proper backend system to be able to support both the be able to support the so-called your requests for your deep learning inferencing models. So I hope that answers your question. So Liu Wenta has a question. How do you for digital data? Okay, so maybe thank you for. So the question is this: I've shown a lot about digital data, or rather, of images or images. What about other forms of digital data? So I'll share this. Other forms of digital data, or rather, all image data is digital data by itself. Every single pixel that we see as an image is actually converted to a form of digital number. And so whatever you see there is already in a form of digital data. If you're talking about text, deep learning as well is able to carry out things like natural language processing and also so-called word generation, which are sentiment analysis. These are topics that I didn't cover for today, but I can share with you this. In 2013, that was where we first had our big breakthrough in deep learning, and that occurred in the image space. So at the point of time, the accuracy for object detection was about, I think, 70, 80+%. But the deep learning model actually improved it by more than 10%. And that was the first breakthrough, first time that deep learning was so apparent in terms of the accuracy breakthrough. Following from those years, we now see that this the way that deep learning is being used in image started to expand a lot, and we are in fact seeing that very, very richly done in the industry. The same for text occurred in 2018. So from 2018, they managed to build very strong models, for example, your GANs or transformers, that were able to analyze text data extremely well. And the next few years that we are going to see from there will be the age of text, like what we saw in the age of image that we saw a couple of years back. And another question is, how do we define independent? How do we define independent or dependent variables? So dependent or independent variables will be the variables that you are going to feed into the system. They are typically known as independent variables. So variables that you're expecting the system to come up with, they are typically known as dependent variables. So maybe an easy way to look at it is that variables that you're going to predict will be known as your dependent variable. Variables that you're going to feed into the model is typically known as the independent variables. One is the, actually, Tan had a good question. For deep learning, effective, accurate, what's the minimum data set? Actually, this is an excellent question. There is actually there's a sweet spot, in fact, where classical machine. So if you go back, if you look, if you are able to review the video, you go back to the slide. There's a point of time whereby for small data set, deep learning actually doesn't work very well. So you will have to look into classical machine learning models like random forests or so-called or decision trees or such classical machine learning methods. But at a certain point of time, deep learning then starts to exceed the so-called the performance of classical machine learning models. The exact point where that happens, it differs case by case, and so differs a lot on how you are able to strike, or rather how you are able to arrange or understand or design your deep learning algorithm. Maybe as an example is this, how to say, we now have certain types of data learning techniques that don't require a lot of data. So for example, let's use the example of image, for example. We have very good and established deep learning models in image already. If let's say I want to apply this on a separate type of data, but let's say it's also image, but this image that model was not trained before. So for example, if I want to train it on I want to differentiate between photos that contain my son versus photos that contain my daughter. I want a classifier that's able to tell me this photo has my son, this photo has my daughter, this photo has both my son and my daughter in there. So how do I do that is that I would then, instead of training the entire machine learning model all over again, I will use the existing model that is there, and like use a technique called transfer learning. And if I use the technique called transfer learning, the number of images that I really need for me to rebuild the entire new model isn't a lot. In the example that I shown earlier, the number of images that are used is only about 100 over images. I believe they are also using a form of transfer learning, meaning that they are not building the entire model from scratch, but they're actually using an existing model, and then they are transferring the knowledge from the new data back into the model itself. Now, I hope that answers your question. Let's look at other things. How thoughts on small organization with no in-house data scientist resource can embark? Yeah. So on this, I would like to share this. There are certain organizations in Singapore that can help small firms like what you are saying. For example, AI Singapore, they do have in-house AI engineers, and they have I think they call it the 100 Trees project that's able to sort of to look at certain industry-wide projects that are really useful. That will be one suitable avenue that you'll be able to work with them on. Of course, you can also look for IHLs like SIT or other IHLs as well. We do have our own AI so-called researchers that will be able to help and assist companies like yourself. And I would like to say that being SIT, we are always very industry focused, and we want to ensure that whatever products that we, or rather whatever so-called products that we generate, that we do, is always very beneficial to the industry. Let's see. Can deep learning use? Yeah, of course. So the question is, can deep learning be used in R? Okay. Yes, it can be. It can be used on the R programming language. I would, however, say that R is a little bit more towards the statistical side of programming. The one of the bigger and newer packages are typically written in Python, and they are also specific packages in Python, or rather specific machine learning so-called techniques that are written more in Python. So I would say that if right now you're having a choice between R and Python, probably my biased opinion would be that of Python, but definitely you can also do deep learning in R. Okay, what are the performance metrics that you would use to measure your accuracy for image classifier model? Okay, so for that, of course, you have the typical accuracy measures. So you have the balanced accuracy measures. That can be one. Another one that you would want to look at very closely is actually your loss. So okay, so actually this is a very good question, Emily. So you want to look at your loss very much. Why? Because like sometimes if you are looking at just your accuracy measure, you may be suffering from something called overtraining. So what you want to do is you would first divide your data into various parts. So one strategy is that you divide it into your training data, you divide it into your testing data, and then again your validation data. So that's one of the techniques that you can do. you train your model on your training data first, and then you can start to test it on your testing data. Accuracy is one thing that you can look at. Another thing that is very important is actually the loss that is being generated. The loss is how much difference. It's something like accuracy, but it's how much difference does your, uh, based on a certain metric does your model have between your test and between the actual model and your test data, and between actual model and your training data. And you want your loss to be similar to both your training data and your test data. Okay. But the danger then is the following. If you were to apply it onto your validation data, what then is your loss? Okay, if your loss from a validation data is actually very, very high, what it will mean is that you have overtrained your data to fit that of your training and your test data. So although you want your loss to be as low as possible, but at the same time, you want to ensure that you don't overtrain your model as well. So like what we said earlier, you want to achieve a certain type of generability. You want your model to be able to generalize across various different scenarios. Okay. So Ms. Go Wei Kun, Go Wei Kun has a question, how to deploy a deep learning model. So earlier, just using the example that I put earlier, we train a deep learning model. And then in that example in particular, we are able to export out the model. So typically what we do is, what we do is the following. We first, of course, we first export out the model. And then we have to find a way to be able to access access the model from, so we export out the model as a file, and then we have to find a way to be able to interact with that file. There are several ways to do it. The so there are several ways to do it. Okay, so I'll share on just two ways for today. The first way to do it is we can export it out as executable, whereby you will have another front end system, another software that will be interfacing with this executable. And that is actually one of the projects that I'm also involved in, whereby we built an Excel front end from them. And from the Excel front end, we use it to interact with. So from the Excel, the executive loads in the data. He does all the data management within the Excel front end itself. And then we have a macro that sends the data into this executable. And from the executable, returns back the result back into the Excel. So just from Excel alone, that executive is able to run very deep and complex machine learning models. So that is one of the many ways. Of course, there are different. Another way is that you can put it as you can call it like a backend server, and you can write it as they call it an API service, whereby how to say, you have pieces of code that's able to interact with your model, and you expose a certain internet gateways, so that other programs or other software will be able to interact with your backend system back to your APIs. Yeah. So maybe I won't go into this because it may be a bit maybe not as yeah. I'll just go ahead first. So let's go on. Part-time course for there'll be some that I'll be sharing on later on. To my listing, some deep learning models can be used for. Okay, yeah. So a question: some deep learning models can be used for training purposes. So in terms of image, of course, there's the ResNet. There's something called the ResNet 50, 100, 150. Okay, ResNet is a form of a deep learning trained model. 50, 100, 150 is the depth of the model. Not necessarily the deeper it is, the better it is, because the deeper it is, the harder is it for all the weights to be trained over again. So there are three versions. You have to, sometimes you just have to test to see which version is best for you. There's also VGG, there's also VGG 16. So these are some of the models that are there. These belong to, they call it the object recognition model. There's another type, which is the object detection type. So what the difference is that object recognition means you show a person a certain image. It tells you this is an apple, this is an orange, this is a pear. Object detection is you show the image of a fruit basket. And in that fruit basket, it will tell you at this point, this is where the apple is. At this point, this is where the banana is. At this point, this is where the pear is. So that's the difference between the two of them. And for the object recognition, you can use YOLO will be one of the easier ones to try. There's one by Facebook called Detectron tool. The entire code on how to retrain the model is actually online. You can find that quite easily. Actually, I just used it I think a few months back only. How to okay, this question is also very nice. PyTorch or TensorFlow 1 or TensorFlow 2 for deep learning? Okay, in general, I think try not to do TensorFlow 1 because we are already moving towards TensorFlow 2 already. Okay, in terms of starting out, I would definitely recommend TensorFlow 2 because the documentation, the community is bigger, and documentation I think is slightly better than that of PyTorch. PyTorch, however, is very flexible, so it's very good if you want to design certain models. And I can also share with you, if you look at Kaggle, the top models that are there that run faster or what, they're always, well, not always, I would say, it's more common to see PyTorch modules rather than TensorFlow modules. So yeah, so there's a comparison there. You have to see which one is more suitable for you. But if you are starting out, I would recommend TensorFlow 2. May I know which machine learning software you were using to build the ML pipeline and training testing for your demonstration earlier? Yeah, so in the earlier one, actually, I didn't use any machine learning modules or what. That is a free, uh, a free, a free demo system provided by Google. I think we can show that later to you. So with that, you can actually try at home. You can try at home to just play around with it to just see how that works. But if you're talking about machine learning software in general, for me myself, I use Python in sklearn. So that will be one of the uh, 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 faster way to just to pick up what machine learning is. And then once you're a bit more familiar with some of the terms, how you should be training or using them, you can then move on to deep learning like PyTorch or TensorFlow too. Um, is computer vision deep learning? Okay, so computer vision is actually a very wide topic. What we are seeing today is just one part of computer vision. So computer vision entails at the very beginning you will have all the line detections, all the edge detection kind of a thing. Then right now today, it probably has progressed towards what we are seeing right now, which is image detection, image recognition. So the earlier portions will still you still consider them to be computer vision, but they're probably a bit more of those classical techniques. Right now we have other techniques like deep learning that form part of the entire computer vision arsenal. So uh, uh, there's a question, what are some of the biggest and most important problems deep learning will solve in the next 5 years? Uh, I'm actually very sorry that I don't think I can answer that question. So please forgive me, Susan. Yeah, so I'm go ahead with the next question. Yeah, so Liu Wenta had a similar question. There's a cost to the data analyzed. So when do we need to consider deep learning over classical machine learning? I would say this. Typically, if it's possible first to try the classical machine learning technique, just try that first. If there are established techniques that, for example, in image processing, the first thing I would do would always be deep learning because it has already been tried and tested to work really well there already. For natural language processing, currently right now, I will also be moving towards deep learning. Why? Because classical techniques have been seem to not perform as well with those as of now. So for certain domains, it is very somewhat clear that we should be moving towards that of the deep learning techniques. For other domains, they are still very strong in classical machine learning, And so those will be where you want to stick to classical machine learning first. Okay, so I will use one last, I will answer one last question. So is OCR deep learning? So OCR is is a technique. So definitely there are OCR techniques that. So okay, once again, OCR is a one big vertical by itself. There are various techniques how it can be applied. So there's of course the traditional OCR techniques, and there are also the classical OCR techniques. And one advantage of these deep learning techniques for OCR is that right now they are also building up language models, knowledge models on top of these OCR techniques that allow you to understand after doing the OCR, how are different elements connected to one another. Excuse me. Yeah, so I hope that answers the question. Maybe if there are further, you can ask the organizers or even myself if you have further queries on that. Yeah, and the slides are. Oh, okay. So so I think some of the question was how do we find out more? So in SIT we have the adult education courses. So you have two QR codes there. You can join our mailing list or discover other courses. Personally, I'm teaching. These are the courses I'm teaching over there as well. Machine Learning 1 and 2. Actually, the first two are really received really well. Yeah, doing one new one with Massey University that's going to be happening in April on FinTech. We are also running a course on data engineering in May next year. Other than this, we do have an industry postgraduate program. So if you are looking to do a master's, but or postgraduate so-called degree, but you don't want to quit school, you still want to be working at the same time, and your employee is very supportive of you. You're able to work together with us to actually even draw a salary while pursuing a full-time master's or doctorate degree. There is going to be joint supervision with both industry and the SIT supervisor, and you actually will get the best of both worlds between both academia and the industry. And with that, thank you so much for your time. Thank you so much for HeadHunt for your kind invitation. I'd like to pass this time back to Tammy. Thank you.